Imagine a world lit only by fire and sunlight. Electricity was a mysterious force, barely understood. Most early experiments focused on electricity in solids and liquids, but Michael Faraday looked elsewhere. In the 1830s, Faraday sealed electrodes into a glass tube, pumped out most of the air, and applied high voltage. Instead of a spark, a shimmering purple arc leaped across the near-empty tube. A gas discharge, lightning in a bottle. Faraday's experiment showed electricity could travel through a near vacuum, making the remaining gas glow. Limited by the technology of his day, he couldn't remove more air, but his glowing tube hinted at deeper mysteries. Faraday's work opened a new door, inspiring future scientists to explore electricity and gases. This was the first step toward discovering a hidden building block of the universe. For years, Faraday's mysterious light remained unexplained, until Heinrich Geissler arrived in 1857. Geissler, a master glassblower, invented a powerful mercury vacuum pump, creating tubes with far less air than ever before. When high voltage was applied, the entire tube glowed with vivid colors, depending on the gas inside: neon red, argon, lavender. These Geissler tubes became scientific novelties and the inspiration for neon signs. Inside, high voltage stripped electrons from the cathode, sending them flying through the gas and making it glow. Geissler's tubes offered a window into the atomic world, even if no one yet understood what they saw. His innovation gave scientists the tool they needed to probe the mysteries of electricity in near-empty space. The beautiful colors were clues, pointing toward a hidden subatomic world. Julius Plücker took Geissler's tubes further in 1858, pumping out even more air. As the gas glow faded, a faint greenish light appeared on the glass near the anode. Something invisible streamed from the cathode, striking the glass and making it fluoresce. Plücker brought a magnet near the tube, and the glowing spot moved. This showed the invisible rays were not just light, but charged particles, deflected by magnetism. The rays traveled in straight lines from the cathode, behaving like a stream of particles. Plücker's discovery was a leap forward. These rays had mass and charge, not just energy. He couldn't say exactly what they were, but he'd found the first solid evidence of a new kind of electrical current. The mystery deepened. What were these invisible charged things streaming from the cathode? The hunt for their true nature was on. Johann Hittorf in 1869 set out to prove where these mysterious rays came from. He placed a Maltese cross inside a discharge tube between the cathode and anode and pumped out the air. When voltage was applied, the glass glowed green, except where the cross blocked the rays, casting a sharp shadow. This simple experiment proved the rays traveled in straight lines from the cathode. The shadow showed the rays were not random light, but a directional stream of energy. Soon after, Eugen Goldstein named them cathode rays. Hittorf's shadow experiment made the invisible visible, confirming the rays' origin and path. Now, scientists could ask deeper questions. What were these rays made of? Did they have mass? The shadow on the glass pointed the way to the next discovery. The path to understanding cathode rays was now clear. In the 1870s, William Crookes pushed vacuum technology to new extremes, creating near-perfect vacuums in his tubes. With these Crookes tubes, he confirmed cathode rays traveled in straight lines and cast sharp shadows. Crookes placed a tiny paddle wheel in the path of the rays. When the current flowed, the wheels spun and moved. This showed cathode rays had mass and momentum. They were particles, not just energy. Using magnets, Crookes proved the rays carried a negative charge. He believed he'd found a new state of matter, radiant matter, made of fundamental charged particles. While his term didn't last, his experiments revealed cathode rays were streams of negatively charged particles. Crookes's work set the stage for the final breakthrough. By the 1890s, scientists knew cathode rays were streams of negatively charged particles, but what were they? The answer came in 1897 from J.J. Thomson at Cambridge. Thomson used refined Crookes tubes and measured how cathode rays bent in electric and magnetic fields. He calculated the charge-to-mass ratio of the particles, over 1,000 times greater than a hydrogen ion. This meant the particles were incredibly small and light. Thomson called them corpuscles, proposing they were fundamental parts of the atom. This shattered the old view of atoms as indivisible. Thomson had discovered the first subatomic particle. Soon renamed the electron, it changed our understanding of matter forever. The journey from Faraday's glowing tube to Thomson's electron was a relay of discovery. The ghostly light in a vacuum tube was the glow of the electron, a fundamental piece of our universe, finally revealed.